initial velocity of the body is U. Position or configuration is called potential energy. Then the force applied there is conservative in nature. So the equation of motion independent of time, here work done exclusively depends on the path taken. Hello students, welcome back to the second session on the chapter Work, Power, Energy. In my previous session, we introduced ourselves to something called as work, where we told work was defined as the dot product of force and displacement. We studied the different units of work. We studied the force displacement graph and the significance of the graph, saying that the area under the graph gives the measure of work done. We defined energy as measure of work. And finally, we defined kinetic energy, which is the energy possessed by a body because of its motion. In my today's class, we start understanding a very, very important concept, a key concept for any entrance exam, as well as a question repeated quite often in your board exam, something called as work energy theorem. So we understand a very important theorem, which is work energy theorem. First, I will consider the statement of work energy theorem, and then mathematically I will prove that this theorem holds good in the case of a constant force. So this is a theorem which is very much asked as a 3-mark question in the exam. Now the theorem states that the work done by the net force, or more precise, I use a word, constant force, work done by a constant force in displacing a body, andre in moving a body, in changing the position of a body, is equal to the change in the kinetic energy of the body. Or in simple words to understand, work done by a constant force is equal to change in kinetic energy of a body. As simple as that. Whenever work is done by a constant force in changing the position of a body, in displacing the body, automatically causes a change in the kinetic energy of the body. Now, I will consider a body of mass m which is moving with an initial velocity u. So these are my initial considerations. I consider a body of mass m. M is the mass of the body which is moving with an initial velocity u. Initial velocity of the body is u. Now, a constant force F acts on the body. Some force, constant force, capital F, acts on the body, displacing it through x. And now, the final velocity of the body becomes v. So these are my initial considerations. There is a body of mass m. It is moving with an initial velocity. Initial velocity, what I call as u. It is acted upon by a constant force called F. The body is displaced through x and v is the final velocity of the body. Now, I will consider the equation v square equals u square plus 2as to describe the motion, because I did not consider time into consideration. So the equation of motion independent of time, v square equals u square plus 2as. Now, v square minus u square is 2ax, where x is the displacement of the body. Rearranging this equation, bringing u square towards the left hand side, v square minus u square, this is equal to 2ax, where x is representing the displacement of the body. Now, I multiply half m on both the sides of this equation. Both sides of equation 1 is multiplied by half m. So I get half mv square minus half mu square is half m into 2ax. So in simple terms, both sides of the given equation is multiplied by half m. What I have called as equation 1 is multiplied by half m. Dear kids, observe this equation. Half mv square. Isn't that the equation for kinetic energy? Yes. In my previous session, we have written the expression for kinetic energy, which was half mv square. Since v is the final velocity, this is the final kinetic energy minus u initial velocity. So this expression is the initial kinetic energy equals. Now, observe here, m a into x. So m a into x. Final kinetic energy minus initial kinetic energy equals ma into x. Final kinetic energy minus initial kinetic energy. So this is some change in kinetic energy equals, what is m into a? Newton's second law, definition of force, mass into acceleration, F dot x. Beautiful. X is the displacement. Force into displacement is nothing but work. So here, change in kinetic energy is work done, and this is what we treat as work energy theorem. So what does work energy theorem say? Work done by a constant force always changes the kinetic energy of the body. Work done by a force results in the change in kinetic energy. So, very much established theorem. The result of this theorem, very important for an entrance exam. Please do keep in mind, for the board exam, this is a 3-mark question. Next one. So now we study something called potential energy. If you recall back, we understood the concept of kinetic energy, where we told it is the energy possessed by a body because of its motion. Then what is potential energy? it is the energy possessed by a body by virtue of its position. P for potential, P for position. So the energy possessed by a body because of its position, which in physical sense we also call configuration. Position or configuration is called potential energy. Because of my position, my arrangement, what I call configuration, I possess some type of energy, and that is called potential energy. A body at a certain height above the surface of the earth, because of its position above the surface of the earth, will have gravitational potential energy because its position there, its configuration is influenced by gravitational force. So gravitational potential energy. So we say any body gains potential energy by virtue of its position, by virtue of its configuration, that is called potential energy. And it is given by the expression P equals mgh. See the factors which affect potential energy. Mass of the body. Mass basically defines position, configuration, height. Small g is a constant. So we say here m is the mass of the body, g acceleration due to gravity, h height of the body above the surface of the earth. So very clearly now, distinctly now we understand kinetic energy is because of the motion of the body, because of its speed, whereas potential energy is because of the position of the body, configuration of the body. Examples for potential energy, we say water stored in a tank because of its position, height from the sump, overhead tank. So water stored in a tank will have potential energy. Spring has potential energy. The winds of a watch will have potential energy. So wherever position is coming into picture, wherever configuration is coming into picture, potential energy will exist. Now, again, we talk about a clinical concept called conservative force. Now, what is this conservative force? We say, if the work done depends only on initial position and final position, and independent of path, the force applied is called conservative force. ತುಂಬಾ ಟೆಕ್ಸ್ಚುಯಲ್ ಆಗೋಯ್ತಲ್ವಾ ಡೆಫಿನಿಷನ್. ವಾಟ್ ಇಸ್ ದಿಸ್? ವರ್ಕ್ ಡನ್ ಡಿಪೆಂಡ್ಸ್ ಓನ್ಲಿ ಆನ್ ಇನಿಷಿಯಲ್ ಪೊಸಿಷನ್, depends only on final position, but it is independent of path, does not depend upon path, then the force applied is conservative force. What do I mean by that? For example, I start traveling from point A, which is Mysore, initial point, starting point is Mysore, and I have to reach the point B, which is Bangalore. So my final point, final position is Bangalore. So I start from the initial position, which is Mysore. I have to reach my final destiny, final position, which is Bangalore. How do I travel? All the way straight to Mysore, through Mandya, I can reach Bangalore. Start from Mysore, Mandya, Bangalore. Or Mandya, deviate near Malvalli, take a round trip, go to Bangalore. Or from Mysore, via Coorg, I can reach Bangalore. Here, I am not considering the path in which I move. But what is important? The starting point, Mysore, and I have to reach Bangalore, irrespective of the path in which I move. Similarly, students, if the work done depends only on the initial and final positions, not considering the path taken, then the force applied there is conservative in nature. A more realistic example is gravitational force. An object is at the point A from the ground. Here. Now I have to release that object so that it falls to the ground. So from A, it has to come to the ground. I don't consider the path in which it moves. If I take off, ignore air force, straight. If air resistance in picture, may not travel straight. But my consideration is the initial point A and the ground. So the force here, gravitational force, is conservative in nature. Spring force, electrostatic force, they are conservative in nature. Whereas the other way, when we talk about non-conservative force, here the work done exclusively depends upon the path traveled by the body. If the work done by a system depends upon the path traveled, then the force applied is non-conservative. Example, frictional force, air resistance, etc. Now, therefore, we will now write down some differences between conservative and non-conservative force. Again, in the exam, this is a 3-mark question to compare conservative force and non-conservative force, to write the differences between conservative and non-conservative force. Conservative force, as I told, the first difference is the definition itself. Conservative force depends only on the initial position and final position. It is independent of the path taken. Whereas non-conservative force, here work done exclusively depends on the path taken. Path independent adre, the force applied is conservative. Path dependent adre, force applied is non-conservative. Here work done in a round trip is 0. We say in a complete cycle, round a trip, for a conservative force, work done is 0. For non-conservative force, there is negotiable amount of work done. Therefore, it cannot be 0. Here work done is completely recoverable, retraceable. Here work done is not recoverable. It is central in nature, retarding in nature. Examples: gravitational force, electrostatic force, frictional force, and viscous force. So these are the differences between what we call conservative and non-conservative force. So here again, students, separately, I have listed the properties of conservative and non-conservative forces. By comparison, whatever I have given, I have listed them separately so that it helps you to study for the exam. So in my session, we have very much understood a very important theorem called work energy theorem, features of potential energy, and distinctly to understand what is a conservative force and non-conservative force. So in my next session, I will come up with again an important topic called the conservation of mechanical energy. Until then, have a nice time. Thank you.